So yesterday we talked about the importance of being able to estimate the area under a curve, and we looked at different ways we could do that. All right, I'm going to pick one of my intervals here, and I'm going to make it an LRAM. All right, here is an LRAM, that yellow one. It's an LRAM because the height is determined by the left side, which is smaller than the right side, and so that is an underestimate. A different LRAM, maybe over here, would be an overestimate, because in that particular case, it's a decreasing section of the graph, and that decreasing section would mean that the left side was higher. And so an LRAM here would have some that were too low and some that were too high, but overall maybe they'd kind of balance each other out. Okay, that would be LRAM. We could do RRAM as well. Okay, I'll switch colors, see if I can, I'm going to see if that's going to show up. Okay, I'm going to try a pink color. Okay, I'm going to do an RRAM. Here's an RRAM. This RRAM happens to be too high because for that section the graph was increasing, and so the right side is higher. But an RRAM right next to it on the other side would be too low, again because now it's a decreasing section, and so the right side is smaller. So again, RRAM overall, some too big, some too small. So then we talked about the third way. We talked about doing an MRAM that would split the difference between all of those. And so if I switch to an MRAM, for every single option, the MRAM is going to have partially too high, partially too low. And again, that's going to be better. All right, so my question to you is there a better shape than a rectangle? We've talked about rectangles created on the left. We've talked about rectangles created on the right. We've talked about rectangles in the middle. Might there be a better shape that would fit into that column than just a rectangle? Jason? A trapezoid, exactly. Okay, a trapezoid is going to fit more nicely into this.
Do you find that trapezoid just by averaging the two?
Okay, yeah, we're going to talk about that and how to find that trapezoid for sure. So a trapezoid, oh, I lost it. Where'd it go? Come back. There we go. Okay, a trapezoid would fit really, really nicely into that space with hardly any error at all. Now there is still going to be a tiny amount of error. Okay, but trapezoids are going to fit in to that space really well with way less error than the rectangles did. So today we're going to talk about the trapezoid being maybe a better shape to figure that out. And so rather than just focusing on the left or just focusing on the right or trying to find the middle, let's introduce the trapezoid as being a better shape. All right, so this leads us to the title of today, which is the trapezoidal method. Yesterday we had the rectangular approximation method. This is the trapezoidal method. All right. So, as Luke was reminding us, a trapezoid is just a triangle sitting on top of a rectangle. So you could subdivide this into a bunch of little triangles with a bunch of sitting on top of a bunch of tall rectangles. Or I think it's easier to know the formula for an individual trapezoid. So we reviewed that yesterday. Okay, a single trapezoid is found as 1/2 base times the left side and the right side put together. So that would be height 1 plus height 2. Okay, those are the two sides of the trapezoid put together. It's basically an average of the heights times the base. Okay, now you have a blank drawing there, which we are going to come back to, so I want you to leave that there, but then go down below and we're going to work out a trapezoidal sample problem together. Okay, so let's find the function x minus 1 quantity squared plus 3 on the interval 0 to 4. Use trap. All right, this is a parabola shape. This shape has gone 1 to the right. It's also gone up 3. Okay, 1 to the right and up 3. And so the graph of this is going to look like a parabola that had its vertex 1 to the right and up 3. And then the parabola comes through that. We're going up to the number 4. And so we would want to label the values here to help us create the trapezoids. All right, my different heights are 4, 3, 4, 7, and 12. The trapezoidal method then will have me do 4 different individual trapezoids. So the first trapezoid is 1/2 times a base of 1, and then the heights on the left and right are 4 plus 3. Okay, that gives me the very first individual trapezoid here. Plus, the second trapezoid also has a 1/2 times a base of 1, and its left and right heights are 3 plus 4, plus 1/2 times the base of 1, and then the next trapezoid, the third trapezoid, has left and right heights of 4 plus 7, and the final trapezoid is 1/2 times the base of 1, and its heights are 7 plus 12. And so to simplify the math on this, you'll want to pull out the 1/2, which is constant to everything. You'll also maybe want to pull out the number 1. So I think the math is going to be easier if you think about it like this. 1/2 is pulled out of the 4 plus 3, and then the 3 plus 4, and then the 4 plus 7, and then the 7 plus 12. So those are the individual terms. You may even find it easier to chunk this. Okay, when you're doing some mental math without your calculator, is to say, okay, I've got 3 plus 3, that's 6. And then I've got 3 4s in a row. I've got 4 and 4 and 4. So that's going to be 12. And then 14, and then another 12. So I just find it's easier sometimes to chunk those numbers together. 12 plus 12 is easy to add together. 6 and 14 is 20. So you've got 20 plus 24, or 1/2 of 44, for a value of 22. The same principle applies as it did before. How would you improve the accuracy of the trap method? More trapezoids. Okay? Don't just do 4 trapezoids. Don't limit yourself to 4, but increase that. Okay, would you grab your calculator so we could practice this method with the program? Okay, let's zoom way in on a particular, well, let's pick the 4 and the 7. This graph is concave up. What that means is when I connect the endpoints at 4 and 7 and make a straight line, that would form the top of my trapezoid. Okay. The top of the trapezoid is going to be like this. So the concavity of the graph is pulling that, that bit of the function just a little bit below that perfectly linear line that forms the top. So for concave up functions, trapezoid will always overestimate the actual value of the graph, okay, actual value of the area. Now the reverse is true. If you happen to be concave down, so if for some reason we were working with something that had a concavity that was down, so I'll just draw a little piece, the top of the trapezoid then would be beneath the value of the actual function. And so when you need to justify an answer in an FRQ, it always has to do with the concavity. Okay, is your estimate an underestimate or overestimate? And you would have to say, because, in this case, because the concavity was positive, a trapezoidal method will always underestimate the amount of, will always overestimate. A concave up would be an overestimate in a trap situation. The reverse of concave down would be an underestimate in a trap situation. But you just want to be able to visualize that. Okay, so how do you find it out exactly? So I'm going to introduce a new notation to you about exact area. Trap is only an approximation. Okay, exact area. The notation for exact area is called an integral. It is a symbol that looks like this. Okay, that is the symbol for exact area. We will learn how to find that, but right now we're going to have our calculator work that out for us. If you want to do an exact area, then you put that symbol, it's called integral, okay, just so you know how to pronounce it, the integral symbol. You put the function after in parentheses, please. Okay, so the function would be x minus 1 to the second plus 3, and then close out your parentheses. You need to tell the integral which axis is the bottom, because sometimes we do area that's going to be sideways on the y-axis, but right now we're doing axes that are on the side, and so you put dx instead of dy. That's the notation, and you'll learn a little bit more about that in the future, but for now, that just means that the bottom of my area is the x-axis. And then your interval doesn't get written like this on 0 to 4. That's not how we write intervals when we're using this notation. We put the 0 here on the bottom and we put the 4 here on the top. So we've used trap to estimate that the answer of this is going to be 22. Let's use integral on the calculator to figure out exactly what it is. Okay, so this is kind of like a drum roll moment, I feel like. We got really friendly with math 8. That was n-deriv on your calculator. We're going to get friendly with math 9. Okay, so you go to math 9 on your calculator, and that should pull up the integral symbol. If anybody does not have the integral symbol pulled up, then please see me right at the end of class so that I can update your calculator to the right notation. Okay, and so then there's spaces for you to type in everything. So go ahead and type in 0 to 4 as the bound limits for your integral. And then in parentheses, which are already built in for you, go ahead and enter the function. And then it gives you a blank to specify the axis that's going to be the bottom. And then you hit enter. And it tells us that the exact area is 21.3 repeating, or 21 1/3 is the exact area under this parabola but above the x-axis. Okay, any questions on that using the calculator for that? So trap is only as good as an estimate. The math 9 integral will be the exact value. And then we'll be learning in the next coming days how to do that without our calculator, because right now the calculator is doing it. Okay, one last thing to do on your notes. Okay, back up to that blank graph that you had drawn previously. All right, try and subdivide that the same way that you subdivided the other one. as close as you can. It doesn't have to be perfect. Okay. There's a third shape that was used before calculators were invented. So we've seen rectangles. We have seen trapezoids. And then a man named Simpson experimented with, he said, I want a trapezoid, but I want the top to be curved. I don't want the top to be straight like a regular trapezoid. I want the top to be curved. And so he created a new shape called a paraboloid. And he made the top of his section a curve that even matched the concavity. He wanted to match the concavity because trapezoids missed out on the concavity. So he created something called a paraboloid. There's a whole formula for what he did. I don't need you to know that. I've programmed that into the Simpsons program of your calculator. So this is called Simpson's paraboloid method. And it's even more accurate than the trapezoidal method. The only restriction of Simpson's method is that it only works with even subintervals. Okay, you can't work it with odd. You have to divide your area up into even. So make a note to yourself that it requires even number of subintervals. That's not a hashtag, that's a number. All right, so let's run that on our calculator. You will not have to do Simpsons by hand. But I just want to show you how close this guy was to the real deal without a calculator. All right, for our last thing, we're going to run Simpsons. So remember now, we knew that trap got us 22. The real answer is 21.3 repeating. Let's see how good Simpson did before the advent of a calculator. So go ahead and run number 4. Make sure you put in 4 sum intervals like we were doing from 0 to 4. And he came up with 21.3 repeating, which is the exact answer that you get with the Math 9. Okay, now you can look in the book if you're interested to see his actual formula and how that all works out, how he was able to compute a paraboloid for each of those. But you won't ever have to do that by hand. Only do that if you're interested in looking at it. Okay? All right, so you'll be working with trap. You'll be working with a little bit of simp on the calculator, and you'll be working with the integral symbol to find the exact values of the area for your homework for tomorrow. So I'll see you guys on Wednesdays now. I didn't used to do that, but I'll see you tomorrow morning, Wednesday morning. All right, that's it.